So the first part that we have here, the connection weights are different between the input layer and your output here. However, here we see that all the connection weights, they have the same weight, which is fixed to 1. So for the first row, we have this part, this vector, then this third and your fourth. This was the output of your first convolutional layer. Applying this kernel, and this results in this subsampled output. And we can see that if we consider this first max pooling, so the max is 2, which is our output here for the max pooling. For the next, we have x value 1 for this output. Similarly, the output is 1 for this, and here we have all zeros, so the max function results in a 0 output. So how do we map from this latent output, intermediate output, onto our final output of the subsample space, which will be this? So where did we get this 2 from? What were the input for this 2? We got the input from 0, 2 and 2, 0. So these 2 were the input for this output 2, subsampled 2. Similarly, for the next 1, 0, 0, 1, 1, 0, 0, 1, we get this output 1 and so forth. And here we are not applying any weights, we are just estimating what is the maximum value you have under a specific area of interest. And so we don't apply any weights on this layer. All the weights are fixed to 1. So there is no weight update. No update on your weights when you are doing the pooling. So when we are learning the parameters, at this point there will be no update on your weights. So how we can represent the convolutional neural network in the form of a neural network representation? So we got an image, 2D image. We first passed it through a convolutional layer. Then we did the thresholding. Then we subsampled using max pooling to obtain our final feature map, the first feature map that we have here. And how? And we converted this structure into a neural network representation with weight values on each of the links that are connecting the layers, first layer, second layer, third layer, for example, and we have connections with these layers. So we can say that this is your input, this is your network, and this is your intermediate output. So for the input, we have a neural network to obtain our feature map. So we can replace all these convolutional layers, thresholding, and the pooling layer or subsampling we can represent this as a neural network. We have converted these in the structure of a neural network where the layers have connection weights. So the structure for neural network would therefore be your input image. Then you have multiple representation of your neural network components, which lead to intermediate feature map. Then you have the next layer with components, neural network components that extract the features to obtain your high level or higher feature maps. So we can say that each of these components can be represented by a neural network. And the outputs, here we have the intermediate output. And then we have one more intermediate output, which is the higher feature map. These are the intermediate output. We still don't have the final output, which is the classification. So the overall structure that we have here will become an input image with feature extraction, where each of these networks, it is composed of neural networks, convolutional layer, pooling layer or subsampling layer, and then we have the final fully connected layer, which is the classification head of our neural network. So previously we studied that MLP has a fully connected network, but for the convolutional neural network we have a partially connected neural network, and the purpose is to extract the features for a given input image and classifying your image into some category, digit classification, or maybe image classification. So so we can have a classification at the end using the features that we have learned, features that we have extracted from the images. So example of our convolutional neural networks are face recognition system, identifying different cars, or elephants, chairs. Some of you have given you want to identify certain objects, so you will be using the different type of neural networks, different version of your neural networks to extract the information or obtain the feature maps, which will further be used for your classification. So you would have a convolutional layer, then pooling, then one more convolutional followed by pooling layer. Usually pattern is this, that your convolutional layer is followed by pooling layer, and then finally you have a classification head. You have fully connected network. You can have 1, 2 or more fully connected nodes like the MLP, where all nodes are connected to the previous output. So all the feature maps that we have here, they will be given as an input to the fully connected layer to finally give you the classification. So the general structure of a convolutional neural network is your 2D or 3D image, and you use the features using kernels, using the convolution function. Then you perform the nonlinearity. This is your nonlinear function that could be sigmoid, that could be soft, that could be 10H, depending on your application. So you could have the transformation, nonlinear transformation, and then you can do your spatial pooling. And spatial pooling is basically the structure of your neural networks, and you are doing the pooling based on their position in the feature map. that means by spatial pooling, and different type of pooling are used. Most common are average and max pooling. There are other versions also available, and it reduces your feature map when you do the pooling. And then you do the normalization. We studied before the normalization concept, where we are trying to remove the distortion and have a better classification results using the or normalization factor. We can do the normalization here, and then we could have our feature maps. These feature maps would be input into your fully connected networks, 2 or 3 layers, which would give us the final output, the classification output. So this is the general structure of a convolutional neural network. That we can define. We can also change the number of layers, and there are some well-known convolutional neural net models that can be used as a baseline to compare your own results. So whenever you're going to implement some version of convolutional neural network, you will always have to compare them, and for comparison we could have some existing model of a convolutional neural network, and then you can compare it with that. So this is it for the lecture contents on convolutional neural networks for now. And if you have any questions, and queries, you could email me. And I will be vigilant to answer your queries to the best of my knowledge. Thank you.